All right, in this example, we're going to be proving what we're asked to prove. And I'm going to prove the first thing first. So this says prove that the determinant of A inverse is equal to 1 over the determinant of A if A is invertible and square. So here's what I'm going to do. First of all, I'm going to just start with 1. And I'm going to ask myself, what is 1 equal to? Now, there's a lot of answers to that question, right? 5 minus 4, 3 over 3, pi to the 0. There's a lot of questions for what equals 1. But specifically, what equals 1 that's useful for me right now to try to prove this? Well, I'm dealing with determinants. So I want to go, okay, the determinant of what matrix is 1? Oh, the identity matrix. So the determinant of the identity. Now, depending on the dimensions of your matrix, there are different types of identities. So this proof is not having me put specifically what dimensions A are. And the reason is that this proof should work no matter what the dimensions are, as long as A is invertible and square. But other than that, I'm not going to bother with the subscript n or subscript m, because this could be 2 dimensions, 3 dimensions, 17, whatever, as long as they're equal. Well, all right. What is the identity matrix equal to? Again, what is it equal to that's useful to me? Well, the identity matrix is equal to the determinant of A times A inverse, or A inverse times A, same difference for our purposes. And now we can make some progress. I have the determinant of a product of matrices here. Well, the determinant of a product is the product of the determinants. In other words, the determinant of A inverse is the determinant of A times the determinant of A inverse. And now what I like to do is, well, why did I start with 1? Well, because I was trying to prove that determinant of A inverse equals 1 over something. And so what I'm going to do is I have like my end pieces. Notice they're equalities all the way through. So I can go from here and I can say 1 equals determinant of A times the determinant of A inverse. So the determinant of A times determinant of A inverse is 1. That means I can divide both sides by determinant of A. And if I do that, I get that 1 over the determinant of A is equal to the determinant of A inverse. And that's what I was trying to prove in this part. So I'll put my little tombstone right there. You can use QED if you like. Either way, this proof, the first one, is done. Now, the reason I'm doing both of these proofs is that I can use this to help me out for this proof over here. So let's take a look. I need to prove the determinant of PAP inverse is equal to the determinant of A. Now, of course, we're assuming that P is invertible and that its dimensions are such that it can be multiplied on both sides of A like this, and we get something consistent like that. That's all implicitly assumed. So, assuming this is defined well, let me just start with, well, what's determinant of PAP inverse? The determinant of a product, I use that over here, is the product of the determinants. But you have a couple ways you could do this. And so here's how I'm going to start. I'm going to say, well, this is then the determinant of P times the determinant of A times the determinant of P inverse. Now, matrix multiplication is not necessarily commutative. In other words, A times B doesn't equal B times A for matrices. But these are determinants. And so once I've split it off, where it's just this determinant, this determinant, this determinant, these are just numbers. And numbers, regular old real numbers, are commutative. I can swap the order and it doesn't change anything. So what I can do is I can swap determinant of A and determinant of P inverse over here. And that's exactly what I'll do. So this equals the determinant of P times the determinant of P inverse, just swapping these, times the determinant of A. All right, well, if the determinant of a product is the product of the determinants, it goes the other way around. If I have a product of determinants, that's the same thing as the determinant of the product. So these two right here are the determinant of P inverse, times the determinant of A. My motivation here is that I'm trying to get determinant of A all by itself. And so what I can do is, if I put these together, P with P inverse, well, if I've got a matrix and its inverse and I multiply them, by definition, by what it means for one matrix to be the inverse of the other, it means that when I multiply them together, I get the identity matrix. So this is the determinant of the identity times the determinant of A. But what value is the determinant of the identity matrix? Always 1. So this is 1 times the determinant of A, which is determinant of A. And there we go, tombstone. I've shown that the determinant of PAP inverse is the determinant of A. And how did I do it? Well, I did a direct proof. I simply took what this is, used rules that I'm allowed to use for determinants, split it up, commutative, put it back together. PP inverse is the identity. The identity matrix is 1. 1 times anything is itself, and there I go. This must equal that, which was to be proven. And that was these two proofs.